is present over here had attended the webinar, the second webinar that had happened on 3rd of December?
I did not, sir.
Okay, no.
I
So
missed it.
that means okay, for no issue. Did you gone through the recording? The reason why I'm asking is because that webinar was for the support for the assignment one, and whatever tools and things that was required to come to submit the assignment all these queries were supposed to be um, resolved at that time, because I think this week I think you'll have to submit the assignment. So that's why I'm asking.
Sir, it's
Let me
11th.
check. Huh?
11th.
11th December is the due date.
Acha, 11th. So that means that's near, na? It was
Hmm.
circulated last week, so I think it's near, because that webinar was specifically for the doubt resolution session related to the assignments. Okay, okay, I'll have to update it. So this is for okay for me. Acha, that was the previous date. Okay, no
And
issue.
sir, this assignment is of 7 marks. Mark.
Yeah, there will be two assignment. One pre midsem, one post midsem. So one is for 7 marks, second will be of 8 marks, and there'll be two quizzes of 7.5 marks each. So that quiz comprises of 15 marks and assignment comprises of 15 marks,
Okay.
7.5, 7.5, and then 7 plus 8, so 30. So 30 will be the EC1 weightage.
Okay.
Okay, no issue. No, reason why I'm emphasizing more on those webinars, because it was specifically related to the uh, the assignment and whatever we have studied so far, a small application for it, so that you can have a real-time feeling of how to connect with the data set, how to use that data set, how to perform any activity related to data sets, and all those. Okay, so a data set might change, but the some more or less the activities that we require will be almost the same, as I have already mentioned. Ki whenever because most of the time throughout the course we will be doing some of the other classification activity only, based on different type of model. The model or the internal working of the GNN model will change, but ultimately somehow we will be using the labeled information either with the node or with the edges to predict something which is unlabeled. That's all. This is the whole crux of the GNN or all deep learning algorithm. Okay, whatever you say. So, okay, no issue. You have a sufficient time to still look into that assignment. Okay, because the thing is, we will not be meeting next week, because I have already taken this session priorly on 21st of December. So this is the last session before the midsem regular. Chalo, no issue. Let's move further. So let me quickly brief you what we have covered and what we are going to cover now. So till now, we have started with the, because this is last session, so I'll have to summarize all the content also. So right from the beginning, we started with the type of graph that we will be handling in the term of visualization, and then various numerical values which we can extract out from the graph. So right from the simplest one, which we call it as degree, take a degree, centility, diameters and all. And then we move towards the higher order from the towards the eigenvalue centility, then betweenness centility, then closeness centility. Then even we move towards the triangles and what was it? Equivalence. So regular equivalence and structural equivalence. Okay. So somehow we were trying to find out a number. Then we move towards the similarity. Okay. So graph similarity and node similarity, how similar those two nodes are. And then we move forward. Okay. And then I think we also talked about graph transformation and Fourier transformation and graph signal processing. Okay. So it was nothing. It was converting one type of information into the another, so that we can use the another, or we can say not another. We can use the other good thing about the deep learning, good other concepts of deep learning, and we can implement them into the graph. Okay. Ultimately, the basic thing is for the classification purpose. Okay, so this is the whole story right from the first session till the seventh context session. Okay, so we have not even started with the graph neural network, but we have covered all the topics, all the keywords I have explained in full detail that you will be using, or we will be using for for performing or building up a model to do any of the activity. Okay, so then in that case, nothing will be whatever the keywords which I'll be using, nothing will be new to you. You will have an idea, and first assignment also covers or also tries to find out those small things into the graph, so that you can have a feeling ki, this is the thing, that this is how we can implement. Ultimately, in many of those models, or we can say the platform network X and PyTorch, and I think Python, most of the activities can directly be done by the tools. The pre-compiled function or library functions are already available, but the concept is necessary, because the model, or we can say the library functions which are already available, the precompiled library function which are already available, they will just simply accept some parameters and they will give you some other output. The internal activity will be a black box for you. You would not be able to visualize what actually that library function, that module has done. Okay, so suppose why it is being required, why not it should be a black box. The reason is, if you know what you're doing, and if you know how it is being computed based on some existing model, then it's good. You need not to learn about the internal activity. But somehow, if you're building a new model, and obviously you all will be doing it in your own organization, because you all are at the senior level, and somehow either you will be supervising the activity which your juniors will be doing, or if you are a part of that team, then you will be doing those activities. Now you know that this library function will give me this type of output. But if somehow that model gives you a wrong output, or we can say the model gives you an output which is not expected, then you should be in a position to identify which all are the parameters. Usually we call it as a hyperparameters in this case. So how to why, well, if you tune those parameters, the output will vary. Okay, but you may not be knowing, if you doesn't know the concept, that if what is happening actually if I'm tuning this parameter, what actually that model, what is a change that has been done, or what is a change that happened into my model by tuning that parameter. So suppose, for example, one variable or some constant is alpha. So what is the physical significance if I keep the value of alpha to be 0, or alpha to be 1, or alpha to be 0.5? What if I keep it alpha to be very high? What is if I keep alpha to be very low? What actually is happening inside the model, so that it is giving me output? In a black box, if I tune the parameter, the basic thing is ki, if I doesn't want to know, then I just tune those parameters. I perform the experiment with various values of alpha, and then find out the result. Whoever give me the best result, I will choose that. Oh, this give me this parameter value give me the best result, so I'm keeping it. But if somebody asks why that had happened, you may not be knowing. So to answer those questions, you need to have the clear-cut understanding of all those numerical values which the model, or we can say the module, will be computing. So that's why I was emphasizing more. So, and my basic intention was not to, because that itself can be done by chat gpt. Okay, but chat gpt cannot tune. ChatGPT cannot adjust by himself. It is humans that has a capability. So that just by looking at the values based on our experience, we can identify, oh, this might be the possible reason. Okay, so that's why we have invested too much of time on those concepts. Getting a model working is a different thing. Okay, but understanding a model is a different thing. Now the second scenario is, currently we are facing that issue. We were working on a some small subgraph mining on a uh, biological data which we use for the cancerous detection. So we are working, me and Professor Vipin and one more professor is working on that model. So that model was not performing well. Matlab, we were not getting the expected output. So we just tuned those parameters. Some results was improving, and but beyond that point, the in spite of getting the best result, we the population matures in between. The what we call it premature. Okay, so we just make some changes by increasing the number of we just tune those parameters by increasing the number of hops from 1 to 2. The moment we increase the number of hops, the program crashes. The reason when we try to identify, the reason is key, when we increase the number of hops, then in that case, the total number of data points was in millions. Okay, and that program crashes not because of the number of nodes, because of the the data that we were generating. That becomes huge, and because of the memory crisis, the program crashes. So that was not because of the logic were good. If we increase 1 hop to 2 hop, that means we are increasing the neighborhood size. We will be learning more from the larger number of neighbors. But that crashes because we were storing those edge sets based on some text file, okay, separately, some edge sets. Okay, then we try to reduce the size of the data that we were storing, that we were capturing, building it in one file, or storing it in some CSV file. Even storing it in a CSV was not reducing our or what was not resolving the issue. Okay, so we tried some other method, then we tune it, then we actually, until unless we actually look at the internal working, we were not able to understand ki even there was a small difference, there was a small problem in the code. Because of that, the program was crashing. Okay, so we were using the library function for writing some code, we was using some chat GPTs, and also that was working fine. But because of the internal working of one activity, we were not getting the correct result. Still we're not getting it but to the optimum, but still that results have improved. Okay, so this is what I'm trying to convey, until unless you have a clear-cut idea of all what is happening, you won't be able to, you will be able to give the minimum work, but not a satisfactory one. Okay, it's fine. So let's not beat around the bush. I've already wasted around 15 minutes and I started the recording. Sorry. Okay, so let's move ahead. So data as a graph. Now we'll be moving towards the, today we'll talk a bit about the, we can say heterogeneous graph and the knowledge graphs. Okay, and then quickly towards the end of the session, we will start with the GNN, graph neural network. Okay, so formally, these are data as a graph. Explicitly, either we'll be working on a social transportation, even for the brain graph, web graph, molecular graph, and the gene graph. So this will be a various kinds of graph. Now, just have a look till now. So in this case, till now we were talking about the homogeneous graph, where a single type of node and a single type of edges. Okay, now if I want to store some extra information into the graph, for example, in terms of social graph. So the first thing is, we are also differentiating the users based on their genders. So some are male, some are females. Okay, so the male interaction on a social media, like on WhatsApp or a call, is something different. Whereas female to female interaction pattern is something different. Male to female interaction is different. Okay, pattern. And female to male communication is also different. Okay, just on the lighter side, if there are two boys who are fast friends who are just connecting together and they want to plan something. Okay, so one will send a question mark to other. Okay, and the other will send a time, and the third and the person will again gives a thumbs up, or even no thumbs up, just a time, he just viewed it, and they will meet at that point. Okay, so none of the, if we analyze it, so question mark, time, and then something happened. So that interaction pattern is something different. Woman to men, men to men, men to women, there will be a different type of interaction. So ultimately, if I need to have different attributes related to nodes as well, so different types of node as well as different types of communications. Okay, so just in this graph, if you can just look, if you can zoom, I cannot zoom, you can zoom this portion, and you can see that there are different types of gender wise and even look wise also. Some maybe, or if we based on the geographic location or something, so some brown skins, some blue skins, curly hairs, whatever it be. So we can have different properties associated with those nodes and their interactions. And even some communications are like this, some are box, some are something like this. So there may be different type of communication on, and we can say different attributes related to that graph. Okay, same as the case, although this is a transportation, one connects to another, but that can be through cargo, that can be through, matlab, if this is an air transport communication, so air transport communication through commercial flights, private jets, we can say commercial flights, and defense, we can say defense vehicles, and many more things. So there can be different types of nodes in a transportation graph as well. For the brain mapping also, different type of communications, nerve signals to different types of, or we can say different areas of body. Okay, so heart may send some different signals, sorry, brain may send some different type of signals to heart, some different type of signals to lung continuously. Okay, because they work throughout the life. Okay, but brain may send different type of signals to the hand, fingers, and many other things. Okay, so ultimately, even for the molecular graph as well, now we'll be looking at in terms of different types of node and different types of connections. So for a molecular graph, till now we were just talking about like this benzene ring and all. Okay, so okay, we were slightly differentiating it based on the single bond and double bond, but somehow, so there was default. Now if there are a compound and the compound interact together, so this red may be a one type of node, purple can be the different type of node, green may be a different type of node, and they are connected to each other with a different type of edges as well. So in reality, in a social media graph, we will not be dealing with the homogeneous graph. We'll be dealing with the heterogeneous graph. Same as the case with the molecular graph. Same as the case with the transportation graph. Brain mapping. Okay, for the web graph as well. Different type of communications. Gene graphs. Some different types of genes connected to each other with a different way or different pattern. So in that case, okay. So that was the data as a graph in an explicit way for a human. In terms of implicit means we will not be giving a photo to the computer or to the model, and the model itself will create a graph of a different type. No. Okay. Same as the case with this one also. We'll not be giving them just a photograph. Okay, this is the model. This is the molecular graph. You design the network by your own. No. Ultimately, we as a human will be storing the graph in some or the other form of representation. So either in the form of adjacency, multiple graphs, and many more things. So if this is an image, it can be represented in the form of the we can say intensity label, RGB values. Okay, so so ultimately, if you can look at, okay, so in that case, those graphs have been taken from this resource. Okay, as well as this is being taken from this paper. So you can just have a look. If I'm talking about the relationship, okay, so pairwise relationship means metrics in the form of tensors, temporal pairwise, directed pairwise, weighted pairwise. Okay, So there'll be some sample weighted directed graph, temporal graph, dynamic, heterogeneous graph, and many more. Okay, if it is higher order relationship data, so it can be a sequential diffusion, it can be a time series data, it can be a group data, and so on. So different types of data and different types of connectivity. So if we'll have to apply the machine learning on a graph, so a numerous real world problem can be summarized as a set of tasks on a graph, either in terms of ultimately all of them in terms of classification. So link prediction means edge classification, node classification, community detection, ranking, and so on. So if I have to implement some machine learning algorithm on the graph data, so the graph has to be represented in the form of features or in the form of a matrix. Okay, so now that traditional IID data that can be used for classification, clustering, ranking, and many more things. So this is the whole, we can say, not super, just an overview of how we will be implementing. So the main thing is now, as of now, we will be focusing on this activity. How to represent the data, the graph in such a way that it can be used for any of such activity. Okay, so the basic thing is how to formulate the scenario, how to formulate the graph in such a way so that we can set up a model for any of such activity. Okay, so if simple graph either in the form, so this is the way how we can store the simple graph, vertices, edges, and this is the whole graph. So graph is a collection of vertices and their interconnections between them. So if I'll have to convert them into form of a signal, that graph will be converted into some vectors of real numbers. Okay, so this is the vector of real number of order n. So n will be a vector matrix, which this f1 represent to the feature vector of node 1, f2 is the feature vector for node 2, f3 is the feature vector for node 3, and so on. So this will be a simple one, easiest way of saying. Actually, we will not be storing it in this way. Just for the visualization purpose, I am saying that okay, we will be storing in the form of a vector, in the form of we can say feature vectors. Okay, if it is a multi-dimensional, then the mapping will not be of order n. The mapping feature vectors will be of mapping of order n cross d. What is d now? D is the dimensions of the node vector. We can say, or ultimately in broader sense and easy way, these are all the properties associated with those nodes. Okay, that we are recording. And based on that, we will be analyzing or we will be building up our model. Okay, so in an easy way, we till now we were saying in this way, but actually each node also have some attributes. Each node has also some properties. Still easy because we will be having the properties associated with this with the edge also. Okay, but as of now, let's slowly and steadily make the thing difficult. So let's start from the vectors, from the node. Node may also contains some properties, some attributes. So that mapping has to be done. So that mapping will be of order n cross d, and again this will be real numbers. Okay, set of real numbers. This I think I have already talked a lot. So if this is the current graph, based on that we'll predict okay, what should be the, whether there should be an edge between them or not, whether there should be an edge between them or not, but like a recommendation system or something like this, whether we should recommend this product to not product. If I'm talking about simple graph, so friendship network. Okay, if in terms of label, so it can be in the form of link prediction as well as is in the form of a node label label classification, or we can say node classification. What should be the color assigned to those nodes which are unlabeled? Okay, so somehow this is our model. Somehow that model has worked and assigned some labels to the nodes, or had suggested where there should be an edge between those two nodes and net. Okay, so these are the activities on a structured graph data node level. So either link prediction or of graph or node classification, or if we'll have to perform it on a graph level, then we'll call it as graph classification. I think we have already discussed a bit about it. This is label 1, this is label 2. So based on that, how to identify that, okay, so if this is which label to be assigned to which type of a graph. Okay, still superficial, we will be diving deep into each activity later on, but I have, as of now, I'm just giving you a cover. Multi-relational data and knowledge graphs. So we are given with a multi-relational graph, I think as already. So in that case, the edges are defined as a tuple, U and V. So these are the endpoints of the edge, and tau is the particular relation, that the property that it holds between those U and V edges. So now edge will not be edge will not be we can say will not be just start node and end node. It also have some internal, and that gives me how those two nodes are related. So so the indicating the presence of a particular relation tau, that will be a different set, will be an element for a different set from the T. So tau holding between those two nodes. So such multi-relational, so that how the two nodes are related, and there can be multiple type of relations. So such multi-relational graph are often referred as a knowledge graph. Okay, since we can interpret the tuple UV with respect to tau as a specific for a particular fact that holds between those two, okay, type of connections between them. I'll try to explain you through a small examples. So suppose, for example, this is the graph which I have taken it from this paper. In this, there are different nodes, and nodes are connected to each other by some edges, and this is a directed graph. Okay, but just have a look. There are nodes. So David Beckham is a human. Victoria Beckham is a human. Harper Beckham is a human. Okay, so those are the three humans which are connected somewhere. And there are few other nodes which talks about something different. England is some country. London is a state. Football player, that can be the professions. Actor is also profession. Designer is also profession. Harlow, I don't know where it is, but it is a city. Okay. Now this node is being connected to several other nodes with a different types of edges. Some may be unidirectional, some may be bidirectional. So David Beckham has a nationality in England. Okay, so humans are connected to the node of a countries with the property of nationality. Born in, this may be the relation. So this is the city. So David Beckham was born in London. David Beckham has different professions. He is a football player. He is an actor. Okay, so the connectivity is now profession. He's connected to another human, which is Victoria Beckham, which is a marriage. So this is a bidirectional edge. David Beckham is married to Victoria Beckham, and so Victoria Beckham is also married to David Beckham. Okay, now if this is a unidirectional edge, so he may be married to someone, she may be married to someone else. So it can be a different. In that case, that relation may have a difference. So it may be divorced or relationship, whatever it be. Okay, whereas Victoria Beckham has one daughter. So this edge, now they both are connected to one node. Okay, they may share a common profession also. In that case, this can be. Okay, so it's not so okay. It can be if two humans are connected to another human, that can be some relation. So the relation is daughter. Two humans are connected to one profession, so that means they may be sharing a same profession. Okay, he was born in somewhere else. And so this is a one example for multi-relation graph where a multiple types of node. Okay, some may be countries, some may be professions, some may be countries, some may be cities, and so on. Now, okay, fine. So that's one example for a knowledge graph. Actually, most of the graph that we will be work, or actually real-time conversion of a graph will have all such properties, and we'll have to take care of this. Same like social media graphs. Okay. The another example for heterogeneous graph is this. So this have been taken from this paper, graph heterogeneous multi-relation recommendation. Okay. So there are some different type of users, male, females, and kid. There are different type of, so these are again a node, and these are different type of node. Okay. McDowell's, KFC, Harry Potter, and recommendation system. And they have different, they have a different types of nodes as well. So this may be the food chain. This also a food chain. This may be the vegetarian. This may be the non-vegetarian. This may be, we can say, or something. This KFC. I'm not sure. I've never again gone to KFC because vegetarians. This is not the place for vegetarians. No point of reaching there. But somehow, okay, a different types of node. This is a Harry Potter. This may be a book or a movie or CD, whatever it be. And this is a recommendation. This I know. This is a book. Okay. Now, users have different types of interactions also. So user one views McDowell's. User one views KFC. Somehow he put something on the cart and then purchase from KFC. So even in those two nodes, there are different types of connections. One is view, which can be two other, and can be purchase also. It may be possible that he may purchase something from McDowell's also. Okay. And then add to the cart this book or this movie, viewed this content, and then add to the cart. Okay. He is not interested in recommendation system, but U2 is a different user who views Harry Potter, the view recommendation system, purchases this book and gives the rating. Okay. So, sorry, this is a different kind of edge rating that we also recording. Okay. Then U3 may be a different user who just viewed this book and did nothing. Okay. So in that case, it may be or we can say bipartite mapping. One types of users, one type of set, they are the users, and another type of nodes, which can be the products. Okay. There's no communication between them. There's no communication between them. There can be. So it can be, if there's no communication, it is ensured, then we'll call it as bipartite graph. Okay. If you do remember what we have talked about bipartite graph, a graph is said to be bipartite graph if it is can be partitioned into two different sets such that they are collectively, they are mutually exclusive and collectively exhaustive. And if there is an edge, it has to be from one set to another set. Okay. Or it can be a graph partition also, not specifically bipartite. They can also have some sort of interactions. Okay. So users in terms of book, he gives the rating for this book, and then he likes, he gives thumbs up to his rating to this book. Okay. That was helpful to me or not. Okay. In Amazon, you might have seen if someone gives the rating to the any product, the user gives thumbs up or thumbs down, was it helpful or not, to the ratings of those product, and even to the humans as well. Okay. So it may be not necessary that this partition has to be bipartite. Okay. It can be simple graph partitioning problem also. The another kind of graph inactivity that have taken from this paper, fraud detection using relational graph learning to detect the collision. So this is the for uber.com. So this have been taken. So now a bit complex. There are some vehicles, There are some drivers with a different set. There are some users on a phone. Okay, so there's some phone means application, or we can say some interaction in interactive, or uh, we can say application platform, a platform through which some are connected. Okay, so there are some users which we call it as riders. Okay, and some ratings or feedback or the complaints or whatever it be. Okay, so rider shares something among themselves, right? Riders are connected to drivers through a application platform. Okay, drivers also give feedback to each other. They can also complain about each other. They are associate, they both have something in common. Riders and drivers have something in common, which is the cab, in which they have taken a ride or they have shared. Okay, even there can be different type of riders also, frequent riders, or we can say normal riders, or different labels of riders as well. Okay, so this again is an example for a heterogeneous graph where we have a different types of node into the graph, different types of edges in the graph, and into the graph, and various types of interactions. Okay, so that means if they are connected to each other, they might have booked it. Okay, so in this case, this may be the booking or something. In this case, the riders connect to each other and share something, share their experience to others, and so on. Okay, so this also is an example for a heterogeneous graph. Okay, and actually, whenever we'll be dealing with such kind of graph, all the graph will be of this type. In a biomedical knowledge graph, we might have edge type like threads. Sorry, not threads. Sorry. Treats. Okay, so this tau can be the treats. So this medicine treats this kind of disease. Okay, so they can be a different node set also. So that the endpoint of this treat will always be, one will be the medicine, one will be the disease. Okay, one disease, it may be possible that one disease treats the another one. नहीं, छोटा दर्द बड़ा दर्द जैसा कुछ नहीं होता. But um, U and V, मतलब different type of nodes. Okay, so indicate that drug associated with a node U treats a disease. So one set of nodes will be the drugs, and another set of nodes will be the treats. So generally, in the goal in a knowledge graph completion is to predict the missing edge on a graph. Okay, we can say, so we are given with the graph in terms of this biomedical data, and then the other activity, the basic activity is the predict the missing link, missing edge, or link prediction means which disease can, or which drug can also be used to treat which kind of disease. So relation prediction, but there are also example of node classification task in a multi-relation, so bipartite or multi-k partite graph. Okay, so generalized version of bipartite graph can be the multi or k partite graph. Okay, what is k partite graph? Suppose, for example, we can say, if I say four partite graph, so four partite graph means the four different kinds of nodes which have their interaction among themselves, but no interaction within the network. Okay, so generalized version of bipartite graph is the k-partite graph. So not all knowledge graph completion methods rely on embedding, and will not cover every variations of the embedding methods. Okay, there are many. So how we can say the situation become complex, or how we actually should record. So this is the plane graph. We have a different, some nodes which we call it as shoes, some nodes which we call it as colors. Okay, some other nodes. Okay, and some broad categories. So if so, shoes can be broadly classified into two: sneakers. Because I'm not able to see clearly. So sneakers and the running shoes. If you want, you can zoom that section. Okay. So there are two different categories of shoes: sneakers and running shoes. This is the type S1 and S2, maybe the classification. Then the color, brand, style being promoted by certain celebrities. Okay, so this may be the colors. What is the color and what is the brand? Okay, so bike or road universe and so on. Now this is the same plain graph. It's the knowledge graph will be they all this can be a bit more complex network. So they all belongs to the shoes, has a subclass of boots and sports shoes. Boot also can be further classified into high boots or low boots. Sports shoes, sneakers, running shoes. Those this is almost the same. Okay, the type S1, S2 promoted by certain celebrity. Then it can be a different color, so it can be indigo, blue, what type of blue, cold blue, light blue, whatever it be, hot blue and warm blue. Okay. Even S1 and S2, they may have a different kinds of brand, and these are the colors: bright crimson, orange, warm orange, then colors. And also they so this is the we can say in the way by which we can further represent the graph with full detail. With full interface means who is matlab, how they are connected to each others, and some more details about their connectivity. Okay, so this may be the explicit and this may be the interface. Okay, so simple graph, a knowledge graph out of it, and with the interfaces. Okay, which all belongs to which class or superclass or subclass and so on. So in a multi-relational setting, we also see a diversity of decoders and the loss functions. I think you are aware about. I think you have gone through the um deep learning or machine learning course, so you might have an idea about decoders and loss functions. Do you have it? If not, we will be dealing with those details shortly. This is just a slide. So nearly all multi-relational embedding methods simply defines the similarity measures directly based on the adjacency tensor. Wherever we have the vector, so we vectors representation call it as tensors. Okay, so that is all. The method here assumes that we are trying to reconstruct the immediate neighbors from a low dimensional embedding. Okay, this can be ignored, I think, because I have not included, I've not explained those keywords, so it is there. So let us first talk about, but okay, you can read it. Some may be directly understandable and some may be confusing. So we'll be looking at it. Okay. Now, first of all, we will look at the embedding. Embedding is nothing. It is the representation of a graph in a low dimension. So an embedding is a relatively low dimensional space into which we can translate high dimensional vectors. Okay, so high dimensional means, what does a high dimensional means? Means vectors with multiple attributes. Okay, so that dimensional means that if you do remember are n cross d. So this d is nothing. This is the vectors with a higher dimension. Means the set of attributes or set of properties associated with that node or with that edge. Okay, different types of node, different types of edges as well. So it captures some of the semantic, meaning semantic of the input by placing semantically similar input close together. Okay, so that in the embedding space as an n is a vector of floating point numbers, vectors of real numbers. Now we are converting them in some form of representation, in some form of coding. We call that coding as an embedding, because we will be using this embedding to process the properties associated with those nodes, but in a low dimensional one. The reason why we want to convert into a low dimensional space, because if I take care, if I include all the details um, separately in some arrays and all, and our graph will be very huge. So that will be the crunch of space will come up. So that's why our main intention is to, without losing much of the information, we have to represent all the details related to those nodes and edges in a lesser space. Okay, but with the condition that the distance between two vectors measured their value, means smaller distance suggested a high relatedness. So if some nodes, some embedding nodes in the graph, we have converted into the embedding, some form of coding, such a way that that coding also captures the information about or those attributes of those nodes and edges. Okay, now those embedding into low dimensional space should not be, should be in a should be as such that if there's a small distance between the embedding, because ultimately embedding means some form of numbers. Okay, some form of numbers, numerical data only. So if there is a numerical data, then definitely we can add and subtract the details. Okay, subtract the embedding. Okay, such that if there's a small distance between two embedding of a node, then that means that two nodes are related to each other. Okay, so it's not the case that we randomly assign A, B, C, D, E in that way. Okay, no, that embedding should also captures the relatedness. So if I subtract two values, suppose for example, if I'm assigning the numbers, okay, easy way, 1, 2, 3, 4, 5, 6, 7, 8. I should write it correctly. 5, 6. Okay. Now I've used those numbers to assign the labels to those nodes. But is this labeling correct? Most probably that's not satisfying this, because if I subtract 2 minus 1, 1 means okay, they are at a distance of 1. 3 minus 1 means suppose somehow they are a slight far away from each other. Fine. 1 minus 4 minus 1 means 3. So that means still farther. Okay. In this case, it is okay. But 1, 8, it should be 8 minus 1, 7 means it is farther. But this is directly connected. So in that case, just if I label 1 to 3 in order of their occurrence or something, that embedding, that may be the default embedding, but that embedding will not work because this criteria will not successful. Is not correct in that case. So small distance suggested a high relatedness. Here relatedness is the distance between them. Okay, it may be multiple attributes, it may be based on the properties as well, node similarity and many other values, closeness values, between the central key values, and many more things. Okay, so that means if there's a small distance between them, those two nodes are similar to each other, much similar to each other. They are highly related to each other, whereas in a large distance suggested a low relatedness to each other. Okay, so I think that's clear. So it is used as an output to downstream the machine learning tasks such as a node classification, link prediction, and k-nearest neighbor similarity graph construction. Okay, we'll talk about this graph construction later on. Wherever we'll try to construct a graph artificially such that it looks like real. Okay, AI generated activities, AI generated graph. So embedding should captures the graph topology. Topology means structural information about the graph. Should capture that. The other thing that embedding should capture is relationship between nodes. Fine, I think we have also talked about it, and further relevant information. Few more. However, embedding should capture this inherent information of a graph fixed. It depends upon the question we ask about the network. So that again, what is important to us, how we are, or in what sense we will be processing those node embedding, or we will be processing that graph. So suppose if I'm talking about node classification, then the properties of those nodes matters a lot and their interconnectivity. If I'm talking about something else, we can say fraud detection something, then in that case, type of connectivity will be more important. Okay, and some more. Although weird example, but some that was the first thing that kept that enters into my mind. So if and then in that case, if you want to learn more about those embedding, these are the papers that are arranged in a chronological order, right from 2013 to 2016. So distributed large scale. Okay, you can read it. So no. But the most important thing is, I request you to go through this paper because this contains much relevant information about the embedding. Node to vector. So sorry, node to vec, he come up with the, he suggested a link is there. Okay, when you will click on it, it will take you to that link. So this is a way by which you convert a node into a vector. So scalable feature learning for network. Okay, and this I think we will be using much. And the second will be the walk, deep walk. Okay, and then the third will be this. And then if time permits, you can also read 1 and 2. Okay. Any questions so far? Sorry, I was continuously speaking, but I have not asked for any doubt. So any clarification required?
Uh, I was a bit confused on your Uber case, use case that you showed, with driver and uh, images. If you go, so I still feel like it looks to me like a knowledge graph more than a multi-relation, and the reason being is, so the driver will always ask for a ride, and it will go to the user will ask for a mobile, through mobile it will go to the driver. So it's always the my edge is always fixed here. So why are we calling it a multi-relation graph when my edges are already kind of type is kind of fixed? Generally, like I see is multi-relation graphs. The other use cases that you showed, where the node type was not fixed to, yeah, like this one. But in this Uber case, we already know it's kind of fixed only. So I was a bit confused, like why are we considering it a multi-relation graph?
Mhm. Fine. Okay. Nice. Um, Normally, there's a very thin line of difference between the multi-relational graph and a knowledge graph. Okay. Most of the time, they can be used interchangeably as well. If you want to convert this multi-relational graph into a graph, then you can assign. So although this graph doesn't contain much of the detail, so driver gives some feedback to others. So this may be the text or a call. Okay, so either someone complains about the driver through a text message, someone complains about the driver through mail, someone directly call a call center and makes a complaint. So there can be different types of feedbacks as well. Okay, and there can be different types of drivers based on the ratings, different kinds of riders based on their ratings. Okay, so for example, some may be the new customers joining the network. So in that case, if their experience is good, okay, so if their experience is good, they may continue or they will continue with that services. If in the first ride itself they found some difficulty, then most likely they will drop from the network. Even there are some set of users who are very frequent. Okay, like in your in the flight, or we can say airport mechanism, they have a frequent flyer number. Okay, so that means frequent flyers are given a bit more privileges as comparison to the newcomers. Okay, So they can be different. In that case, uh, they can be used interchangeably, but this graph does not show most of those details. It can be of different types of edges as well.
Got
They have
it.
not
It's how you perceive it. We have not defined the edge to what it is
ah,
here currently. Okay.
this may be a partially labeled graph, or we can say incomplete graph. So that's why some missing detail we call it as multi-relation. But with the full detail, I think like this one, where it is, Shuvala. Here it is. So simple. It is a partially graph. We call it as plain. We can say heterogeneous graph. But when we include most of the details, the labelings and
Then
all
it
those
would go
things, then it can be a knowledge graph. So in that
knowledge.
case, we can say that knowledge graph is a subset of the multi.
Multi-relation. Got it. Thanks.
Okay. Okay. Any more clarification required? Okay. So we were discussing PyTorch at the start. Okay. So thank you, Batindu. So this means you have attended the class. So how to generate embedding for a particular node with attributes? So Bhupendra, you're asking me? Acha. Nahi, theek hai. So in that case, this is what we will be covering up. So a node, the embedding, I think, is it so? When is our third webinar? Okay, third webinar is, okay. So what I will do is, third webinar is on 13th of January. So to answer your question, what I can give you a theoretical idea. Normally we use one hot encoding, which use the we can say gray pattern नहीं कहते उसको क्या कहते हैं gray coding, okay, such that the distance information is being uh, uh, captured. But what I'll do is I will request Professor Vipin to take half an hour session, because he is much more expert regarding the real application of this graph. Okay, so we'll have a small in between. He'll pitch in my regular session, and he will give you a lot more practical ways of generating those embeddings. I can give you the easiest one. We call it as one hot and encoding. Okay, so the name may looks difficult, but the easy way is we use some sort of gray coding. Okay, with a bit changing by flipping by bit sequence, flipping by one bit to its neighborhood, so that number of bit flip can be by calculating the number of bit flips, we can identify how close two nodes are. Okay, so it just that one hot encoding stores the, or we can say convert the embedding of of a graph in a bit sequence, but just by using the bit sequence. But there are few more, so he will be very well explaining it. Somehow. Oh. Mm. So they also might have used, okay, fine. So in that case, sports code, blue code. Acha, ठीक है. Hello. Let's move ahead. Mm, ठीक है. So So till now we have discussed a diversity of methods for no. Sorry, we have not. Uh, Sorry, because I planned this. I planned the one session of Professor Vipin in between, and then unfortunately that didn't happen because I was requesting him. I think this session. This session I was requesting, but I think he was not available. So that's why. But the session was his embedding session was embedded prior to this slide. Okay, so that's why. So we will discuss. Okay, but this we have discussed. Okay, so decoders and the embedding that we haven't discussed, this he will be. I've given you a brief idea about the one hot encoding we can, and I think Bhartendu nine, who was his Bhupend nine. So Vikram has given you a brief, a bit of idea. Okay, about the embedding and their finding difference, but we have definitely we have discussed about the similarity one. Okay, and we have not discussed about the loss function. So ठीक है, ये मिसमैच हुआ मेरा क्योंकि ये मेरे प्लान के बीच में था उसके बाद इनको आना था. Okay, no issue. So decoder gives the score between the pair of node embedding. Okay, how close they are. Easiest way, one hot encoding. Similarity function define what kind of node to node similarity we are trying to decode. Okay, so some kind of similarity values. And then there's a loss function which tells us what is the difference between the output of the decoder and the actual truth of the similarity. Means how correct our model was. Okay, so that difference means what the model has predicted and what was my correct output, ground truth. Ideally, the difference between those two was called is called as loss function, and our main objective is that whatever we have generated should be very close to the actual value. So the loss function has to be minimized. Okay. So lecture 6 means previous one, but there's a mismatch because plan was that he will discuss this node 2 back and all. Okay. That's my mistake. That's a mismatch between the content. But the loss function will be something like this. L will be for all the nodes of a graph. So UV that belongs to the D. Okay. So some sort of we take a negative log. Okay, I'll give you a clear-cut explanation why we take a negative. Why we first of all why we take a log for it, and then why we take a negative log. Okay, but that is the difference between the embedding. Okay, I think I should also discuss with we'll call it. Is it there? Okay, ठीक है, it is there. Where I'm discussing about the gross entropy नहीं, marginal नहीं. There's one more keyword which is pending. Where it is? Just give me a minute. I think I have changed the slides, or some slides are missing, or I may have. Acha, in the case where I was to discuss this, I also used to discuss. The intention was to explain the latent variable. Okay. Okay. So There's one more keyword that I missed to explain is the latent variable. It is very much related to the embedding. Okay, or we can say low dimensional embedding. What is a latent variable in statistics? Okay, or I think in your data mining course, IDS course, you might have gone through this course. Are you aware about this keyword latent variable? Are you ever? No. Okay, fine. Okay. I think it was. Okay, no issue. Okay. Now, latent variable is something which can be observed based on the data, but it cannot be directly calculated. It look confusing. I'll repeat again. Latent variables are the variables which cannot be directly calculated, okay, but it can be observed or it can be measured based on the data. For example, efficiency as a teacher. Now, if someone have to measure the efficiency or how good a teacher I am or goodness of it of being a teacher, then in that case it's not just a number. Okay, so it's not the case that I we can say it is not the just based on the number of courses I have taken, or just based on my face. If I'm good looking, I may be a good teacher. If I'm not, then I may not be. I should not be, or something like this. Okay, or the second scenario can be the satisfaction level. How satisfied I am with my current life or with my current job, or how satisfied a person is in a relation. Okay, so in that case, it is not a measure, it's not a numerical value. It's not a numerical value. Just give me a minute. I'll have to take this call. This is a departmental call. Just give me a minute. Sorry, am I back? Am I audible?
Yes, sir.
Am I audible? Please. Okay. Yeah. So let us continue and quickly finish this. Okay, we were discussing. Sorry for that break. It breaks my continuity. So we were discussing about the latent variable, and I think the example that we were discussing about the satisfaction level. So if someone have to, so if my boss or the owner of a company want to capture the satisfaction level of their employees, so it is not just ki just by looking at their face they can say ki, or just by looking at their dressing sense they can identify ki are they satisfied or not. No. So that means that value, that satisfaction level between scale of 1 to 10 or 1 to 5, or how satisfied I am with my family, how satisfied I am them with my friends, how satisfied with them with my job, how satisfied you are with me as a teacher. Okay, so that will be a number between scale of 1 to 5, 1 to 10, whatever it be, but that depends upon a combination of many factors. Okay, so all those factors, it can be if I'm talking about as a teacher, then there'll be some questions and those questions will be weighted. So I think in my feedback, whenever you will be filling the feedback, there'll be some questions like this: had the faculty come prepared for the session, had all yes or no, always, or sometimes, or some ratings, so always, sometimes, never, or something like this. So every option has some weightage. Has the faculty opened the class on time? Has the faculty resolved your doubts on time or not? Has the faculty was able to perform the evaluation on time, and so on? And in that case, you are asked to give, you will be asked, and you might have been asked to give the ratings based on different always, mostly, most of the time, not always, never, or something like this. Okay, then someone takes a weighted average of all those answers. Okay, and in that case, has he taken all these sessions? Had he taken extra session? Had he taken more effort to explain you something like this? So there may be multiple questions, and then um, each question may have a different weightage. Okay, so suppose some question may have a lesser weightage. So suppose, for example, ki was he were able to resolve nahi, some questions which may be less important. Okay, so in some question may be very important. Was he able to resolve the doubt? So if a faculty is able to resolve the doubt, or be able to explain the concept in an easy way, then that means his teaching capability may be high. He may be he may be we say suppose irregularity. Okay, although he is a good teacher, okay, but he comes in a class 5 minutes or 10 minutes late and finishes the class 5 minutes early, but within the duration of those 1 hour 30 minutes, so he takes a class of 1 hour 30 minutes, but in that 1 hour 30 minutes we were able to explain the content with other professors might be covering it in 2.5 hours. Lazy professors like me who stretch the things and try to explain it in details. So, and someone is able to explain the same thing in an 1 hour 30 minute, then his rating maybe matlab this we can say duration of the should be given less importance. So in that case, what I'm trying to convey is there will be some numerical values. Okay, and each there will be multiple factors, and multiple factor will have some numerical values. Same as the case with the attributes. Okay, there will be multiple properties, multiple attributes related to each node and each edge. Okay, or nodes or edge, or nodes and edge. Okay, both the information we are clubbing, and then somehow we are aggregating that information. Okay, in a weighted average, and then we are coming up with the rating, faculty rating. So faculty rating of as a professor comes out to be 4.2. Okay, so that means 4.2 is not bad. Okay, if someone has a rating 4.9, that means he's a very good teacher. He may not be taking full classes, full 16 classes. He may have taken only 15 class. He have cancelled one class and have taken leaves 10 minutes early and starts 10 minutes late. But Still, based on the other factors, his rating may be high. So those type of variable, the satisfaction level and all those things are called as latent variable. Okay, and that depends upon multiple factors. So if it is in the form of variable, okay, single value, it can also be in the form of a vector. Okay, so if it is in the form of vector, we call it as latent variable. Okay, and the space, we can say the set of all the value or the all possible values or the range of all those numerical values will be called as latent space. Okay, just like similarity values and all. Okay, so clear with this latent variable. And in graph embedding, we will be coming up with an embedding in the form of latent vectors. Okay, so those latent vectors will be a output of the embedding activity, and we will end up with a vector. We call it as latent variables or latent vectors. Clear? I hope now I was able to make sense. Please confirm if I have not confused you.
I am confused at least. I'm not sure about others.
Okay. So but ultimately, malab, the thing is ki what we are doing in an embedding. Where it is
Bending we created
what we are doing in an
embed.
embedding,
We are just creating this
low
vector.
dimensional,
Yeah.
low dimensional vector space. Okay. So low dimension, why low dimension? Suppose, for example, actual node contains, so this may be the, we can say, where is this? There may be, do I have that slide in which it has been mentioned? No, just give me a minute. I will give you, I'll come up with that slide where it is. I think I have missed one slide. Is it reconstruction loss? Just give me a minute. I've already invested full time, but link prediction में आएगा या node classification में. I'm trying to search for an example where I can have a graph with multiple nodes and no, not in link prediction. In the edge node classification, do we have that example? Here it is. Sorry. Okay. But no, not here also. Here. There may be different types of attributes associated with a node. If I'm talking about the chemical data, so what all are the, for every atom, there are a number of attributes. So atomic number, this will be a number. Okay, chirality, degree, formal charge, number of hydrogen atoms, number of number of red radicals, hybridization, is aromatic, is in a ring. So some may be the numerical value, some may be the binary value, yes or no. Okay, so some may be, and some may be in terms of categorical data. Okay, so in that case, properties associated with every node need not to be a number. That's the example which I have taken for the satisfaction level, the feedback which you will give to me towards the end of the session. Well, every value will be numeric. Okay, based on the option that you choose. Every option will have their own weightage, and at the end, somebody will be finding out the average weighted average of all the values. So that time it was easy. Somehow we'll have to find out the weighted average of all the answers and then come up with the rating. But it is not always that all the properties associated with those nodes as well as with those edges should be numeric. Some may be numeric, some may be categorical, some may be binary. So somehow I will have to come up some better way so that all the informations can be represented in the form of, where it is, in the form of vectors, numerical values, categorical data, binary data, but they all should be converted into the form of numerical values associated with each rows. And in clubbing all, we'll call it as vector. Okay, so in that case, and that too, not all. Okay, so we'll not be recording all the data in an easy, it will not be our latent variable be of the order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so of order 12, some 8 cross 3. We'll have to we will have to perform a dimensionality reduction. We'll have to come up with some formula which contains all the informations about the properties of those nodes as well as of the graph, but in a lower dimensional space. So low dimensional vector space. Actually, it was a very high dimensional vector, but somehow I'll have to convert it into a low dimensional space without losing the information, without losing the important information. Okay, so those type of vectors, low dimensional vectors, low dimensionality reduced, no dimensionality reduced vectors of an actual space will be called as latent variable. Now, was I able to convey?
Yeah, got it.
And what is it? Acha, no, this is just a this is a combination of those neural network, different layers of a network. Okay, so this is the actual data which converted into a low dimensional vectors. Okay, so this is how they have encoded, and then they are represented in a smallest dimension, which we call it as latent space. And then, so decoder encrypt the details into a low dimensional space, and decoder decrypt the information, the actual information that was being stored or that was being converted into the latent space into the tries to be as an original data. Okay, so input data dimensions are reduced into the form of latent variables. We call it as latent space. So this is an activity of the encoder. Encoder encrypts or creates the embeddings. Okay. This and this embedding is used by the decoder to reconstruct the whole graph. Okay. So this is the graph. Now output should be a graph. The original graph converted into a smallest one. Okay. And then the smallest information or encoded information is being decoded back by the decoder to reconstruct the original graph. Obviously, there'll be some loss. Okay. There'll be something missing because some data might have been missed. Okay. So the difference between the input data and the reconstructed data, the difference in the both the graphs will be called as the loss, and our main objective should be that this loss has to be minimized. Means the encoder should perfectly reduce the dimension of the data, okay, to a minimum space, and decoder should be capable enough to regenerate the actual graph, tries to regenerate the actual graph based on the latent information available, such that the reconstructed graph, now I'm not talking about the data, it should be a graph. So the reconstructed graph should be exactly the same as of the original graph, but it should not be, it will not be. Ideally it should be, but practically definitely some information may have been missed. Okay, so that means the difference between both the graph has to be minimum. Okay, so thank you, Rajat, but thanks for this example. I have taken this, but this is regarding the data. Let us understand this based on the graph. Was I able to satisfy now? Is your satisfaction level high? Yeah, okay, that's okay. That was part of a joke. But was I able to resolve the query now?
Yes, sir. I think it's fine now. Let's. Yeah.
Okay. So in that case, this is regarding each edge. Okay. So now let me explain this expression. So latent variable is clear, latent space and latent variable. So we'll have to, this loss function is for all the edges of a graph where u and v are the nodes, such that the embedding of node u and node v, okay, minus gamma of some function, some log of this function. Okay, so here denotes the logistic function, sigma denotes the logistic function, p and v denotes the distribution over the set of v's. We assume that gamma to be gamma is a positive number, and it hyperparameter, and okay, fine. I think this may be a new term. I'll explain what does Monte Carlo means. Okay, but our main objective is that the loss function has to be minimized. The reconstructed graph should be almost similar to the original graph. Okay, we'll look at each term in detail, but this is an overview that somehow we'll have to minimize the loss. Okay, and there's one more term, Monte Carlo. In an easy way, any experimentation is said to be Monte Carlo if moving from one state to another state, making any changes into the graph, does not depends upon its past data, past state. So all those situations are called as Monte Carlo. Okay, whatever decision you are making at the current stage should not be affected by the previous one and should not affect the future one. So that means at every point the choice is independent. You are free to make your own choice. There is no one to pressurize you. So all those type of activities are called as Monte Carlo activities. नहीं नहीं नहीं. That is not Monte Carlo. That was, sorry, इरेज करो जो भी ये पुराना था, वो छोड़ो. मोंटे कार्लो क्या था, कुछ कंफ्यूज हो गया मैं. ठीक है, मोंटे कार्लो को छोड़ देते हैं.
Markov property that was.
हाँ, that was Markov chain. सॉरी, मार्कोव चेन. मैं कंफ्यूज हो गया, सॉरी, मेरी मेरी गलती. मोंटे कार्लो का कॉन्सेप्ट, मोंटे कार्लो में
So Monte Carlo is something that taking the example till the episode ends, taking the samples till the episode ends, something like that.
Random sampling.
Yeah, random sampling.
नहीं, I'm just, क्योंकि अगर एक बार मैं कंफ्यूज हुआ हूं तो I'll not, तो let me come back and then in the next lecture I'll explain what does a Monte Carlo, मतलब easy way what the Monte Carlo means. Okay, मैंने मार्कोव चेन मॉडल को मोंटे कार्लो बोल दिया, मेरी गलती. I'll come back to this later on. आज बहुत गलतियां हो रही है मेरे से. Okay, now we'll talk about reconstructing the multi-relation. So given you are given with the embeddings of each node uv and sorry zu and zv, so our goal is to reconstruct the relationship between these nodes in the presence of mult. Okay, we argument our decoder to make multi-relation by accepting a pair of nodes embedding as well as the relationship. Okay, so that accepts the this thing. Okay, so r cross d cross r into r cross d, that gives me a positive real value. So we can interpret the output of this decoder as a decoder. Okay, and the likelihood of that edge exist in the graph and okay, whether that graph should have that edge or not. So the simplest and the earliest approach when learning multi-relational embedding, ये शायद गड़बड़ इसलिए हुआ क्योंकि मैंने वो वाला टर्म बीच में नहीं किया, क्योंकि मैंने अज्यूम किया कि वो हम कर लेंगे, लेकिन वो गड़बड़ हुआ. ठीक है. So fine, with this decoder we can train our embedding. ठीक है, आगे बढ़ सकते हैं, ये हम बाद में दोबारा कवर कर सकते हैं. एक्सप्लेन विद यू. अच्छा, ये सारा कुछ बाकी बाकी की सारी स्लाइड्स इससे कनेक्टेड है, तो आई शुड नॉट स्किप इट. बट मैंने ये किया नहीं है, पढ़ा है नहीं, तो हाउ कैन आई यूज इट. चलो ठीक है, लेट अस मेक अ, ये छोटा सा गैप हुआ जिसकी वजह से ये गैप, मतलब ये भी प्रॉब्लम आ रहा है बिकॉज ऑफ दैट स्मॉल सेशन ऑफ हाफ एन आवर. ओके, so decoder क्या, the work of decoder is that they give you, they come up with matrix of order r cross d. Nine. Just give me a break. Let me have a small break, have a glass of water, and then I'll come back. I think I'm making a mistake, so I should not confuse you all. Just give me a break for 2 minutes. Can I take a break for 2 minutes?
Sure, sir. Why not?
Sure,
This
sure.
first time. Yes. Okay. Okay. So we'll meet at 3:21. से क्या हुआ? ये मुझे स्टार्ट करना था इस बार. हाँ, just give me a minute. I'll start. ठीक है. So, in that case, without wasting much of the time, because I think I have missed some important detail, so that's why that I'm not able to continue. Matlab, I'm not able to generate the pace in the delivery. So what we'll do is we'll skip that topic. I'll come back to it. Hardly 10 slides are left. Okay. So I'll come back to those because some keywords I have not explained, so I cannot use it directly. And if I do have to explain it, cross entry loss and all those things, so in that case, it will take a time. And my intention is because I want to introduce the graph neural network in this session before the midsim. So we'll take the rest of the session post midsim over here. So I'll let me put a mark. Okay, so we'll stop over here. We'll take this post midsim in context session 9. Okay, so these terms will not be, so that means this implies that this content
Will not be part of midsem.
So I should not use any keyword which I have not taken before. This content will not be a part of midsem.
That's
Regular,
good. It's
but
pretty, yeah, it's pretty complex.
but midsem regular. I'm not guaranteeing for the makeup one because for the makeup time I would be able to cover it.
Got it.
Okay. Okay. So I'm stopping over here. Because my intention was to start with this session to give you a brief introduction about the neural network, GNN. It should not be the case that I'm continuously beating around the bush and covering up the basic concept and not starting the GNN. So, although again, this is not relevant, but we have discussed, somehow we have talked, not discussed, we have briefly talked about some of the approaches for a low dimensional embedding. Okay. So now we'll turn our focus for a more complex encoder. We call it as GNN, okay, which is the general framework for deep learning on a graph data. So if I would like to explain it, this is the easiest way I can say about the complex course of graph neural network. So what we want to do, so the basic objective is, so here we want to generate the node representation, means node embedding, okay. Matlab, the representation means embedding somehow that take care of the structural information, means ultimately whenever I'm talking about the structural information, means I'm talking about neighborhood information, neighborhood details. of each node. And the feature information of nodes means 9. Sometimes nodes and edges, or sometimes nodes or edges. So end or edges. Okay. So structural details as well as the attributes associated with those nodes as well as edges, if we have any. So till now, if I compare it with the time series or the other image data, which is they are well structured. When I'm talking about the times sequence of data, I can have one of deep learning. If I'm talking about the image data, I already have the other model of deep learning. Okay, we already have, but so they both are well structured. Either they can be represented in the form of table or they can be represented in the form of a grades. But the problem with the graph data is that it can neither be in the form of series or it can neither be in the form of images. In images, the moment I'm talking about the images means the matrix, the information, okay, the pixel information. Sorry. Now, reason, if I'm talking about the image, so the information or the property of a particular pixel at an image. So suppose, for example, if I'm talking about this one, so the color intensity and all is somewhere similar about their neighborhood. Okay, except the nodes at or the pixels at the borderline. Okay, so borderline of the this image or whatever it be, rest all will be almost similar. So all the neighborhood, okay, all the 8 neighbors will have some values, and most of them will be same or similar to the current node. But the graph cannot be represented in the form of a grid. Okay, someone can say, okay, fine. Suppose if this is the data, this is again some form of network. Okay, that's also in the form of we can say connectivity. But in an image data, this node, the properties of this node have nothing to do with the properties of this node. They need not to, or they will not have a direct connectivity. But in a graph, it can have. Even the leftmost node of the graph, the first node of a graph, can be directly connected to the last node of a graph. So this, if my, because the graph can have this type of connectivity, so in that case, grid, we can say this grid cannot capture this. Grid information cannot capture the graph data completely. So that's why we call it as that's why graph data is something different. So graphs are irregular and thus introduce a new challenge. So these are the challenge in terms of connectivity. So neither in the form of grids, nor they can be represented in the form of a sequence changes. Someone can say dynamic graph. So graph at that point A and graph at the point A plus T. In that case, but that can be in the form of a series, but it is the processing of a graph with respect to 2 different instances of time. Okay, so that's why a time series cannot be confused with the dynamic graph. Okay, so in that case, the usual traditional method that we have learned in the deep learning, either in the form of CNN or in the form of RNN, cannot be directly applicable. So these are the challenges. And the fundamental assumption behind the machine learning on a graph is that the target of prediction should be invariant of the order of the node of the graph. Okay. Now, this is an important problem, a point, as well as a problem. Okay. Now, suppose, for example, what does this mean? This means that if I give them this model, this graph, okay, and I ask and I implement some GNN model and predict something, it gives me some value. Fine. If I give him this graph with different labeling, okay, I know as a human, both the graphs are isomorphic to each other. Both the graphs are same, or even for the same labeling, but with a different orientation. Then my model should not consider this, and this as a 3 separate graph. My model should be intelligent enough to check and to verify if they are the same graph, then output should be same. Means the output for this graph, and this graph should not be different. That can only be possible if my model is invariant of the rotation or the order of the nodes in the graph, or the order of the graph. Okay, so this we call it as permutation invariance. If you change the orientation of a graph, the model should not consider this as a different graph. Okay, so I'll have to perform the isomorphic testing first of all. This is the basic and necessary activity that we'll have to do. If the graph is isomorphic, then I need not to invest time on processing it again, or my model should be able to process the isomorphic graph in the same way as it was for the original graph. Okay, so that we call it as permutation invariance. It should be capable enough of dealing with this. So in particular, the output of a given GNN should be independent of how the node indices of a graph are assigned, and thus in which order they are processed. So GNN requires their parameters to be independent from the node odd ordering, and are shared across the entire graph. Okay, so if I change the orientation, the output should not vary. So the primary challenge is to develop a complex encoder for a graph structural data. Is that our usual deep learning tool? Okay, so either in form of CNN. CNN works well for the grid structure, which we cannot use for the graph data. We have the RNN model, which works well for the sequence, which cannot be used for the graph data. Okay, so if I'll have to deal with the graph, we'll have to define a new kind of architecture. Okay, and what the architecture should be, it should be in the form of some odd ordering. Okay, this is what. So in that case, we will be using the graph itself to generate the structure, the layers based on the neighborhood. I'll come back to this later on. Let me cover 2 more slides. Okay. I hope I'm not overshooted. Okay, okay. So I'll finish those 2 slides. So there are some key terms: multi-layer perceptron. Okay, so that's again those neurons connected in a multi-layers. So it is a fully connected dense layers which transforms any input dimension to a desired dimensions. Okay. A multi-layer perception is a neural network that has multiple layers. To create a neural network, we combine neurons together that the output of some neurons are the input of the other neurons. Okay, fine, clear. They should be permutation invariant. So the function does not depend upon the arbitrary ordering of the rows and columns in the adjacency matrix. Okay, ultimately the orientation will be in the form of adjacency matrix only. Permutation equivalence means the output is permuted in a consistent way when we permute the adjacency matrix. Okay, so that means we have not discussed, although we should have done. So that missing of that half an hour is creating a lot of problems. Okay, so in that case, even if I make some changes, so the formula for permutation invariance is PAP transpose is equals to FA, means the orientation should not have any impact on the output. Okay. The second thing is, if I make some changes into a graph, they should also be reflected into the embedding and in the same order. So we call it as a permutation equivalence. So ensuring the invariance and equivalence are a key challenge where we are learning over graph. So this will be a problem that we'll have to deal with this. Okay, so in that case, we define the deep neural network over graph and we call it as GNN, graph neural network. So would be to simply use the adjacency matrix, we'll be using the adjacency matrix as an input to the model. And then using this adjacency matrix, we generate the embedding of the entire graph. How can we? So in that case, we could simply flatten the adjacency matrix using the adjacency matrix and feed the result of that to the embedding, those multiple layers. And this will be our latent variable. Okay. So that means for adjacency matrix for node 1 and all those. Okay. So these are the different vectors, different orders. So here AI is a row adjacency matrix and this is a vector concatenation. So somehow I have converted a graph. So first row, second row, first column, second column, third column, and fourth column, and they all are concatenated together. This is the easiest one. But the problem is that it is not permutation invariant. If I change the orientation, the output will vary. So we'll have to deal with this scenario. And I'll finish this and then I'll wrap up. Okay. So the defining feature of the basic GNN model is it uses the neural message passing. Okay. So neural means the message passing across the network. So neural message passing, in which the vector messages are exchanged between the nodes and they are updated using the neural network. Now, which nodes we'll talk about and how the message has been updated, we'll again talk about in the next slide. So this fundamental GNN model can be derived as generalization of a convolution to a non-Euclidean data. Okay, fine. Now, why it is for a non-Euclidean data? Because what is a Euclidean data? Euclidean data is nothing in which we have some form of numbers. Okay, either in the form of sequence or in the form of a matrix. Okay, and we can perform the addition and subtraction on those values. So that we call it as that's easy for Euclidean values, Euclidean data. But graph data is non-Euclidean. Reason being is if I am working on a graph and I merge two nodes, I can also perform the merging, the plus operation on a graph, But merging on a graph, merging of two nodes of a graph is something different from adding two values. Okay. Two atoms, when they become a molecule, they may have a different set of properties. H and the Cl may have their different properties. H as an atom and H2 as an atom and Cl as H2 as a molecule and Cl as a molecule, chlorine as a molecule, Cl2 as a molecule may have a different properties. But when they are merged together, this compound has a different set of properties. So it's not the case, okay, दो valency इसकी दो valency इसकी ऐड कर दो या इसकी मैग्नेटिज्म पावर 0.2 है, इसकी मैग्नेटिज्म पावर 0.3 है, तो टोटल इलेक्ट्रोमैग्नेटिक पावर 0.5 हो गई. It's not the case. So that means we cannot add the properties or attributes of two neighboring nodes if I'm merging them. So that's why the graph data is non-Euclidean. I cannot perform the addition, subtraction, division, and multiplication simply on the values. Although there will be values, but I cannot do that. So that's why that data, that's why we are calling it as a non-Euclidean space. Okay. Differentiable variations of a belief propagations. Okay, fine. I think we have talked about belief propagation in the node classification activity. And analogy for classic graph isomorphism test. This we'll have to come up with something in an easy way. So this can be done using an algorithm. We call it as WL algorithm, Wishfar-Lehman algorithm. I hope I have, I'm still within the time. No, I have overshot it by 2 minutes. Okay, so I'll explain this. Can I take 2 minutes more to just give a brief overview how the GNN or the neural message passing or how to convert a graph into a network? Can I take 2 minutes more? Yeah. Yeah, Manoranjan, I'll answer a question. Let me explain this. So if this is my input data and I'll have to convert, and my target node is A. I'm working on node number A. Now, how to convert a layer GNN, or we can say layer of neural network based on the graph. So we will be using the connectivity of the target node itself to convert them into a layer. So if A is my target node, I'll have some form of aggregation of mixing the details from the neighborhood from the different layers. But who will be the layers of we can say first layer for node A? So the first layer will be the direct neighbors. So neighbors of hop one hop neighbors. So one hop neighbors of A will be at the layer one. So who all are the one hop neighbors? B, C, and D. So B, C, and D will be the at layer one. Okay. Now layer two, one hop neighbors of B. So who all are the one hop neighbors of B? A itself and C. So second layer for B will be, so there'll be for different neurons. So there'll be a different network for each neuron. So this is B will be considered as one neuron. So the second layer for neuron B will be the one hop neighbors of B. So who all are the one hop neighbors? A and C. One hop neighbors of C. One hop neighbors of C are A, E, F, and B. A, B, E, and F. And one hop neighbor of the neuron at the layer one at D. So one hop neighbor of D is A. So this will be layer 2. Okay, so this is how, if I have to build up one more layer, then neighborhood of A, neighborhood of C, one hop neighbors only, one hop neighbors of A, one hop neighbors of B, one hop neighbors of E, whatever, whoever they are, one hop neighbors of F, one hop neighbors of A, will be at layer 3, and so on. So this is how we can convert a different neural network, a different layers of neuron, just from the graph data itself. So thank you, and apologies for creating a small mash. That is because of one small session that we have missed. Okay, this was a sync issue because it was supposed to be there finished. That session was supposed to be there in the mid, but unfortunately it was not. So that's why a slight mismatch. But overall, that's okay. So ABCD and CDAB, are they equal? Both are equal. Isomorphic means ABCD CDAB. If it is directed graph, then I think let me answer this. A to B, A to B, B to C, and C to D. Fine. And then C to D, D to A, and A to B. If it is in this form, huh? If it is a, if my original graph is this, then they both are isomorphic. But this answer is specific to the graph given. Is it good? Oh, sorry, I have overshooted by 7 minutes. Sorry for that. So should I stop the recording? We have already overshooted, so I cannot continuously record the session.